So thank you very much, the organizers, for organizing this very nice series of meetings and for inviting me to give this talk. So today I will present selected results, because there are too much results, so only very selected results about the archaeological, what we call the archaeological reconstruction of the radial and global growth of galaxies using the MaNGA SDSS-IV survey. So there are many people involved in these works. We will see when I will be presenting them. So what is MaNGA, first of all? MaNGA is one of the key projects of the SDSS-IV collaboration. It's the acronym of mapping nearby. It's not. Oh, what's happening now? Not going ahead. Just a minute. Probé justo antes y lo típico. A ver. Okay. Okay, it's working. So it's the acronym of Mapping Nearby Galaxies at Apache Point Observatory. This is, in fact, the largest integral field spectroscopy survey of local galaxies, about 10,000 galaxies across 2,700 square degrees in the optical infrared, with a spectral resolution of about 2,000 to 2,500 in the R. So what is integral field spectroscopy? It's a very powerful observing technique that provides spectral information over a 2D field of view. So we have two spatial dimensions, a kind of image, and one spectral dimension. So in this sense, we have a data cube. The product of these observations are data cubes, where we have the spectra in each so-called spaxels. Spaxels are the resolution, spatial resolution that we have with the fibers. In the case of MaNGA, the integral field units, the IFUs, are hexagons, we call it bundles, with many fibers. So for the science projects, typically the fibers, which are in fact those that take the spectra, are five bundles from 177 fibers. These are the most spatially resolved cases, to 19 fibers in each bundle. So from the data cubes, we have resolved maps of spectral features, which tell us about several galaxy properties, spatially resolved, such as ordered disordered velocities. For example, here you can see the velocity maps, emission, a lot of emission lines, equivalent widths of these lines. We can infer with the stellar population synthesis from this information the age, the elemental abundance, the star formation histories, many things of galaxies. The sample selection, again, is not working. Okay. The sample selection of MaNGA is in fact very a little tricky. We observe galaxies up to redshift 0.15 with a stellar mass distribution that should be flat. This is the main thing. We have to. The idea was to have more or less the same number of galaxies in different mass beams, from 10 to the 9 to 10 to the 11.5 solar masses, and the field of view should cover. There are three subsamples. The largest samples, the primary, 47% of the galaxies, should cover 1.5 effective radii of the galaxies. Then we have the secondary sample that should cover 2.5 effective radii of each galaxy. And in order to fill poorly sampled galaxies in the color magnitude diagram, for example, low mass red galaxies or high mass blue galaxies or green valley galaxies, also was planned to do this color enhanced subsample, which is 16% of galaxies, which are up to 1.5 effective radii. So this is more or less the distribution of the galaxies in the redshift magnitude sample. The secondary sample, of course, goes to higher redshift because have to cover a larger field of view of galaxies. Okay, so just to say that the data access already is publicly available now. You can download all the data cubes. There are two kinds of pipelines, the data reduction pipelines, where you can find the reduced raw cubes, or the data analysis pipeline, when you can obtain some derived quantities of the galaxies, the emission line maps, kinematics, and several other things. Here are the links. Or you can use a very nice tool, the Marvin, which allows you to search, access, and visualize the MaNGA data. It's very, very useful, this tool. Okay. There are two main empirical approach to study galaxy raw, completely empirical. One is just, so I will now present some results of our group regarding the inference of stellar population evolution of the galaxies, the MaNGA galaxies. So just to say that the typical approach to study galaxy evolution is using galaxy populations observed at different redshifts and connecting them by means of a statistical approach to recover average properties. For example, here in the lower panel, you have the cumulative mass function at different redshifts. So you choose one mass, for example, the galaxy mass size at redshift 0, 10 to 0.6 in log, and you have a number density. So you can see at higher redshifts the same number density in the galaxy stellar mass functions, and see what are the masses. In this case, you are building the stellar mass evolution of galaxies, Milky Way sizes, let's say, yeah. And even several work, Van Dok, metal groups can even follow how is the inner part evolution of these selected galaxies in different redshift surveys at different redshifts. And the inner part, which is the red one, for example, and the outer part. Here, clearly you see an inside out. But the other empirical technique is when you reconstruct the evolution of observed individual galaxies. In the previous case, it's just statistical. Yeah? For you are observing several redshifts and trying to connect the evolution some way. In this case, in the archaeological case, is the one that I will talk about. You have the galaxy observed today, and you can infer the evolution, at least the star formation histories, the chemical enrichment of these galaxies. In this case, it's very difficult to analyze these data cubes, but the interpretation is easy. You are just tracing the evolution of an individual galaxy. Yeah? For this, we have to use the fossil record method. The fossil record method is basically, the idea is to generate a single stellar population, we call SIN SSPs, just assuming an initial mass function, having the isochrones and spectral stellar libraries for the stars in every position in the Hertzsprung-Russell diagram. And we have a burst of star formation, and we produce the stellar synthesis population, and we can follow the evolution of this population since for example, 1 million years here to 1 giga-year in the red case. Yeah. So this is one only population. But if we have a star formation law and a chemical enrichment law, we can have a lot of this stellar population synthesis, and also if we have a dust attenuation law, we can generate the composite stellar spectrum. For example, at the present day, this is the optical, the blue one is the optical spectrum, which is a composition of many single stellar populations that were produced with this star formation law and with this chemical enrichment law. The idea is to go the inverse problem. So from the observed spectrum, now we can reconstruct the stellar the star formation history or the chemical enrichment history, and this is the idea of these archaeological approaches. Yeah. In 2 words, we use the pipe 3D code. This is the pipe 3D code is a pipeline that reduces the data cubes that using the spectra of a given a given fiber, for example, in a position of the galaxy. Finds the best combination of single stellar populations, which are characterized by ages and metallicities, stellar metallicities, which are the best combination of these single stellar populations that reproduce the observed spectrum. Yeah, and in this way we have the star formation history or the chemical enrichment history from this approach. Well, the first thing I wanted to talk about is how is the stellar mass growth of the MaNGA galaxies. So here I'm showing you the normalized the normalized mass aggregation history. This is time today is here in the left, and this is not the normalized final mass of each radial beam, or in the inset you can see the normalized final mass of total for all the galaxy. For example, most massive galaxies are the red ones, and less massive galaxies are the blue one. So you can see here the clear downsizing trend. The more massive galaxies assemble their stars earlier than the less massive galaxies. But when we can separate in annually, for example, here we show for each mass beam, here we have 4 mass beams, as you can see. For each mass beam, we have the inner, intermediate, and outer radial beams. You can see that galaxies in all the mass beams assemble more or less inside out. The inner beam assembles earlier than the outer beams. But here you have to have in mind one of the problems of this kind of analysis, that the resolution, the temporal resolution at h, let's say, larger than h gigayear is very poor. Why? Because the spectra of all populations is very difficult to disentangle. For example, here you have in red populations larger than 10 gigayears, and in just above is populations about 7, 8 gigayears. It's very difficult to disentangle. So the resolution is not very good for very old populations. But in any case, we did for exercise. So this kind of mass aggregation, normalized mass aggregation history, tell us about the velocity as with which the stars form in the galaxies at different radii. So I can show you, for example, when we divide our sample in early-type galaxies, in late-type galaxies. This is just for a given mass beam, 10 to the 10 to 10 to the 0.7 in log. You can see again here the fact that early-type galaxies assemble earlier than late-type. This is expected, of course, yeah. And when we do this dividing by radii, three different annually radii, you can see that late-type galaxies have a very strong inside-out formation. The inner part, which is the solid line, the blue solid line, assembles earlier than the outer parts. This is an inside-out feature. For the early-type galaxies of the same stellar masses, also there is an inside-out very, very small. There is late-type galaxies have a very strong inside-out. Early-type galaxies, the inside-out is not prominent. So we have this exercise separating not only by types, but also by specific star formation rates or by colors. And and here you have different masses, the low mass in the bottom to the higher masses in the top. As you can see, the inside-out, the downsizing, for example, take by morphological type, the last column, you can see that red are the early type galaxies. As we go to lower masses, the assembly is later and later. So there is a kind of downsizing, but not too much. Instead, for the late type galaxies, the blue ones, you can see the downsizing is very strong. So late type galaxies present a very strong downsizing. And early types, the downsizing also is present, but not as strong as in the case of late type. The same happens with colors. Here are red galaxies and blue galaxies, or star-forming galaxies and quenched galaxies. Yeah, we separated several cases. And the other thing is that the inside-out is more pronounced in late type, blue, or star-forming galaxies than in the red, late, early, or quenched galaxies. So in other work, we try to compare these results with for example, models with cosmological simulations. Only for the Milky Way-sized galaxies, we use zoom-in cosmological simulations with the hydrodynamic code, very high result, well-resolved galaxies. And in simulations, we measured the archaeological mass aggregation histories. That is, we not used how the galaxies are assembled snapshot by snapshot, but just used the stellar particles at the last snapshot and inferred the distribution of age of them in order to have the mass aggregation history. In fact, it's interesting that the archaeological mass aggregation histories in these simulations are very similar to the real ones, to the true ones that we measure snapshot by snapshot. This means that there is not too much migration, or the migration is only 1 to kiloparsec, but in both sizes. This is one result in this simulation. But the point here is to compare these archaeological mass aggregation histories for these Milky Way-sized galaxies. For example, for the MaNGA, again in 3 radii, the inner, intermediate, and outer radius. And here are the results from the simulation. So, in fact, there is a good agreement, I would say. We see in the simulation the same inside out that in the observations. And there, of course, there are also differences. But I would propose that this is a new test for cosmological simulations. Now to compare how is the radial assembly of galaxies. We have now observations for that from this kind of analysis. And so this could be a new test for simulations and semi-analytical models, yeah? But I should do a parenthesis here. The question is, how well does the fossil record method recover really the global and spatially resolved stellar populations of the galaxies? In fact, it's not so good as we would like, yeah? There are several instrumental and observational limitations, the spectral and spatial resolution, instrumental noise, the SING and the PSF, the bundle configurations, which gives the resolution of spatial resolutions, the dithering, inclination, projection effects, a lot of observational aspects that can works or the results from the observation. Also, there are methodological uncertainties on the fossil record, for example, which stellar libraries we use, which stellar evolution models, the binning in age or in metallicity that we're using, extinction, and several things. So in order to explore what are the most relevant problems, we use it post-processed numerical simulation of galaxies and observe it as real galaxies with all the procedures that we use observing the MaNGA galaxies. Yeah, and for example, here I show you how is the age, mass-weighted age as a function of the radius for a spiral galaxy, a Milky Way-sized galaxy. Here are the simulations, and here as you will see in MaNGA. Yeah? Not so good. We lost a lot of resolution, but to this observed galaxy, we apply now the spectral synthesis method, the same that we apply to observations, and try to reconstruct, for example, the gradient of the age of this galaxy. The green line here is the real one that we measured in the simulations. The red one is how this gradient is seen after all these observational constraints, and the blue one is the already reconstructed with the stellar population series. So when we have a lot of good resolution, 127 fibers, more or less is good recovered, the age profile. When we have less resolution, spatial resolution, you can see here already the recovered profile is not so good already. The same is for a bulge-dominated galaxy, simulated galaxy. In this case, because the age gradient in this bulge-dominated galaxy is low, there is not too much difference between observations and simulations within the spectral synthesis model. What about these mass growth histories? How the stellar population, how the stars are assembled radii by radii? The dashed lines are here in this figure, the real ones that are in the simulations. And the solid lines are the recovered So you can see that we lost a little of the inside out. The real inside out in the simulation is wider than the recovered ones. For the early type galaxies, the differences are small. So I will skip this one. Just an example, in this work, we used a completely different code, not the Pipe 3D and the Starlight, to process, to infer the stellar population evolution of the galaxies. This was applied only to spiral galaxies in MaNGA. And what I am showing here is the time at which 95% of the stars were assembled as a function of radius. The red points are for massive galaxies, the green are for intermediate, and the blue are for low mass galaxies. In all the cases, we can see a gradient. That is, in the center are assembled earlier, the stars, that out in the other regions. But in the case of massive galaxies, the gradient is very prominent, while in low massive is almost flat. So this is a result for, there is an inside out for the spiral galaxies, but it's more prominent in the case of more massive galaxies. So let me now go to other series of works that we are doing is with the elliptical galaxies. We can select elliptical galaxies and to see how is the archaeological evolution of these galaxies. You know the scenario of elliptical galaxy formation, the scenario, galaxies have a very, ellipticals have a very early phase, larger than dissipative phase, when galaxies grow by major mergers, gas major mergers, and form very compact and quench, the red nuggets. After that, the non-dissipative phase, minor mergers grow the galaxies in the outer regions. The accreted stars are deposited in most external regions. And the galaxies apparently grow a lot of in radius, but not too much in mass. This is the standard scenario of early type galaxy formation. So the question is, individual archaeological inferences are in agreement with this scenario? So first, we have to select very well morphologically our galaxies in MaNGA. So this is a very recent work. We have a value-added catalog with a visual morphological classification using the DESI image for these MaNGA galaxies, not the sloan, but the DESI images. And so we classify morphologically all the 10,000 galaxies in MaNGA, very accurate. And so we selected now the elliptical galaxies, and we can even select the red and dead elliptical galaxies. So in the color mass diagram, we selected only red ellipticals because there are blue ellipticals, not too much, but there are. And using the equivalent width and the BPT diagrams, we selected only quenched, quiescent elliptical galaxies, not star-forming, because there are also blue star-forming ellipticals. Very interesting object, by the way. But in this case, we concentrate only in the classical ellipticals, red and dead. Yeah, and so in all these plots, the classical ellipticals are the red points. Here, I'm showing the mass-weighted age versus the mass, the luminosity-weighted age, and the ratio of age mass-weighted to age luminosity-weighted ages. As expected, classical elliptical galaxies are very old. The typical age are 10 gigayears, 10 gigayears. But the lower mass are slightly younger. In the case of the luminosity-weighted age, the difference, the low mass are have much lower ages. And in the right, you have the metallicity, the stellar metallicities. So the mass-weighted, luminosity-weighted, and the ratio. And there is the classical that massive ellipticals are very metallic, and lower mass are less metallic. An interesting question is the ratio of this mass-weighted to light-weighted. Why? Because mass-weighted quantities are related to the old populations, because we are tracing the mass, the age or the metallicity of them is related to all populations. While light-weighted quantities are sensitive to late episodes of star formation. So when we plot these ratios, the metallicity mass-weighted to luminosity-weighted and the age mass-weighted to to luminosity weighted, here should be luminosity weighted. So this is the ISO contour show all the 10,000 MaNGA galaxies. You can see there is for massive, for a typically massive galaxy, for example, where are our classical elliptical galaxies here? Are here in this red region, where the difference between the age, mass-weighted and luminosity-weighted age is very small. Of course, mass-weighted age all the time is larger than luminosity-weighted, yeah? But not too much. And what about the metallicities? The metallicities, the mass-weighted, which trace the old population, are larger than the low luminosity-weighted metallicities, which trace a younger population. So this means that massive galaxies, in particular these ellipticals, probably accreted a primordial gas. The younger populations formed from accreted primordial gas from the cosmic web. But what happens with, for example, dwarf galaxies? Here the symbols are for our value-added catalog of only dwarf galaxies, which is led by Mariana Cano Diaz in our institute. And you see low mass galaxies typically have very large, high difference between the age mass-weighted and age luminosity-weighted age, because these galaxies have several late star formation events, and this is why the differences are big. But also the metallicity, the mass-weighted, is all the time lower than the luminosity-weighted. This means that in the case of dwarf galaxies, the young population, the metallicity of young populations is higher than the metallicity of the older population. And why? Probably, probably this is because there is the younger populations form from the processed gas by the same galaxy that is reaccreted. In the case, because the potential, gravitational potential in dwarf galaxies is not so big as to lose completely the gas, and the gas could be reaccreted. So this is a very nice test of these kind of things. We also measured the gradients of age in these elliptical galaxies. Typically, they are flat, and the gradients in metallicity are, of course, negative. A very interesting thing is that we reconstruct the evolution of the specific star formation rate in the inner part, in the outer part. Here we have again 3 mass beams, each panel. And you can see that the inner parts, the specific star formation rate decrease very fast. The galaxies quench inside out, while the outer parts, of course, also decrease, but not as fast as in the inner part. So this is a proof of the inside-out quenching that suffered these elliptical galaxies. And we tried to measure, this is a very hot discussion, what is quenching, blah, blah, blah. So we just evaluated quenching introducing the bit rate parameter, which is the star formation rate at a given time between the average of the previous time. We measured this in our tracks of evolution star formation. And we defined it, we found that the elliptical galaxies, the quenched elliptical galaxies, quench not too early. Here are the quenching time, look-back time, 2 gigayears ago, 4 gigayears ago, 6 gigayears ago. Typically, ellipticals quenched 4 gigayears ago, more or less in average. And we also calculated the quenching time. So the time that it takes the galaxy to quench. And the quenching times typically are about 3.5 years. Elliptical galaxies quenched, the most massive quenched earlier, here are the less massive, and the quenching is relatively 4 or 5 gigayears typically to quench these elliptical galaxies. Also, we were able to measure how is the evolution of the half-mass radius and the half-light radius of these galaxies. Observations in cosmological surveys claim that the elliptical galaxies evolved a lot in radius. For example, here this work by Van der Wel et al. It is the effective radius as a function of redshift for 3 different masses. You see the radius grows a factor of 2 or 3 since redshift 2, from red nuggets to the present day puffy elliptical galaxies. So what our archaeological inference tell about that? So I have to go faster, sorry. So we have found that the mass radius doesn't evolve too much as claim it in this scenario of very fast reduced growth in the non-dissipative phase of this scenario. Here I'm presenting you the ratio of the half mass radius to half light radius for different colors. Just see the orange lines, which is for the R band. So here are, as a function of redshift, I am showing today is here, the past is in the right. You can see that these elliptical galaxies typically at high redshift have more or less the same mass radius to the light radius. But as time goes, the mass radius becomes smaller than the light radius. Up to recently, reached about 0.3, 0.4, when this inverts. We see this trend for all the masses. Only for the less massive galaxies is later. All this behavior becomes later for massive galaxies. And the interpretation of this is that the galaxies are quenching inside out. These elliptical galaxies were quenching inside out. This makes that the mass to luminosity ratio, the gradient of the mass to luminosity ratio becomes negative. This means that the half light radius becomes larger than the half mass radius, becomes more negative, up to the time when the galaxy completely quench, even the outer regions quench, and in this case already the light radius already tend to reproduce the mass. The light distribution already tends to be as the mass distribution because already the galaxy is quenched. Yeah. So this was to explain that, but I will not have time for that. Sorry. And the point here you can see how is the growth of the half mass radius for the different mass beams, the black solid line. The radius grows very almost 10, 20% since redshift 2 to today in this elliptical galaxy. Light radius grows much because of this effect of inside-out quenching, and also because of some aggregation in the outer of younger populations in the outer radius. So our implication of this is that elliptical galaxies probably have an early past evolution without this strong size growth that claims the cosmological studies based on redshift surveys. But there is a lot of photometric evolution. The galaxies are inside-out quenching, are growing in the outer parts. All this cause that the light profile is very different to the mass profile, let's say this way. So just to finish, a few words about global, how is the star formation histories? For example, for different masses, this plot we are showing the star formation histories for very massive galaxies which have a peak at redshift 1 and then decrease very quench. And low mass galaxies, the blue one here, even are increasing the star formation history. These are inferences from these stellar population models. And we can, for example, this very nice plot, we have here the star formation rate versus stellar mass plot. Here are the galaxies, the MaNGA galaxies. We classified star forming are the blue dots, red-tided are the red dots, and the green are the Green Valley galaxies, classified today. How they evolved to the past. You can see here, this is in the past, they were all were in the mean sequence, and as time goes, they are quenching, and today they finish in the, again, yeah, we go again. So we have redshift by redshift, we have this stellar formation rate versus stellar mass diagram for our MaNGA galaxies. Here I'm showing that. And we can see that from the present day to the past, how evolves the mean sequence, let's say. Not only the mean sequence, only the retired galaxies that are retired today, of course, were in the mean sequence in the past. Yeah? And when we correct by volume of the MaNGA galaxies, we can reconstruct, my last slide, the cosmic star formation history. This is the cosmic star formation history. The shaded areas are, for example, the Maddow and Dickinson inference from cosmological surveys in the infrared or in the ultraviolet. Here, the stars, the black stars, is how we reconstructed the cosmic star formation history from MaNGA galaxies after taking into account the incompleteness volume. Aldo worked on that to have this make complete the MaNGA volume. And here we are separating with blue squares are the galaxies that today are star forming, and the red circles are galaxies that today are retired or passive. So you can see how is the contribution of these galaxies to the global cosmic star formation history. You can see that the galaxies that today are retired in the past were the dominant, were in the peak of the star formation, cosmic star formation history. So this is a very nice result that more or less is an agreement, yeah, between completely two different approaches observationally. Yeah? Just to say that now there are two public value-added catalogs with all this information, one by our group, which is led by Sebastián Sánchez in Instituto de Astronomía. You can find AstroPH already this paper. You can find here how to download all this data, the processes with Pipe 3D pipeline. And the other, the competence, is the group, the Firefly. The Firefly, they also analyze the 10,000 galaxies. It's very interesting to compare two different approaches, how are the results. So just I leave my conclusions of, these were just as a few selected results of what we can obtain with this approach, and just I leave my results there. Thank you very much, and thank you for the passment.
I have time for a couple of questions. Oh, sorry, we have time for the two questions. So. Yes.
No, yes. I was wondering, for the calculation of the evolution of the sizes, are you assuming any change in the position of the evolution in the distance to the center?
We are just to show. I think this will illustrate very well. We have maps of different. Let me find just this that I already didn't have time to show. It's here, I think. It's here. The method allows us to have this. Sorry. Okay, just let me show. Here, what I'm showing here is the surface density, the stellar surface density of populations of different age. Here, up in the top right are the oldest populations, and as we go to the low, here are the youngest populations. So we have these stellar density maps of different age, and just we can measure at each redshift the half mass radius or the half light rate, because we also have this mass for the light, yeah, at rest. So what we see is how this half mass or half light radius evolves, yeah, because we have this information, yeah. Yeah, here the main assumption is that there is no migration, that because we are observing only today, and in the case that stars are in the same place, this is, yeah, of course, this is a very important limitation of all these things. Yeah.
Thank you, Vladimir, for this talk. I was wondering about how you classify retired XI star-forming galaxies.
Yeah.
This is my first question, and the second question, two questions in one, is
okay.
In this sample, the MaNGA sample, if there is galaxies within groups.
Okay.
There are galaxies within groups.
Okay. So regarding how to classify galaxies, we have several works on that, but mainly, let me say, I think it's here. we use the information of the lines. For example, the BPT diagram to define which are the star-forming galaxies. Star-forming are those that are below the Keeley line and with equivalent widths, H-alpha equivalent widths larger than 6 angstroms. Retired or quiescent galaxies are those with equivalent widths, H-alpha equivalent widths smaller than 3 angstroms. And Green Valley are those that are 3 and 6 angstroms. Yeah. And for AGNs, yeah, BPT and equivalent widths. And in the case of for the AGNs, we use the 3 BPT diagrams to locate where are the AGNs. Yeah. In this talk, I didn't talk, presented nothing about AGNs, but we have a lot of work on that. AGNs typically are in the Green Valley. It's very interesting thing. Yeah, we have seen. And about the groups, we didn't select. By the moment, we didn't study the environment or those galaxies that are in groups or in the field. Yeah. But there is a valid added catalog of MaNGA by Argudo, where they, for each one of the 10,000 galaxies, have the environment. The groups by Yang et al., for example, and they classify clusters, filaments, voids, or with several methods. They use several methods. Yeah? So, but we didn't use for this work yet the environment. This is one of the things we have to do, by the way.
Vladimir, so to live with the right idea, I got confused in your last slide. You showed us that the star formation history of the reconstructed galaxies had, and you show us ellipticals and spirals, right? And they had the peak of the star formation more or less at the same redshift. Okay, but some slide before.
You mean this one?
Yeah. Okay, blue and red have more or less the peak at redshift.
Yeah, the blue probably, not the blue and the start forming, present day start forming probably earlier.
Okay, okay, present, so spirals.
Yeah, spirals.
Okay. But some slides before there was discriminate. Okay, right.
Yeah.
So what is the difference between these? These are small galaxies.
Small galaxies. Yeah. This is by mass. Yeah.
Okay, okay, that's my.
If you want to see, I didn't time to show, but this is very interesting also. This is with other code, the starlight, with the Thomas Peterkin. We show here, okay, the cosmic star formation history, the total is the solid lines, but here divided by blue, Green Valley, and Reese sequence. And you can see the red galaxies, today the red galaxies are those that most contributed in the past to the cosmic star formation history. And here are the spirals or blue, let's say. Here are the fractions, in fact, time by time, yeah? So we can, and not only also by mass. Here are the shadows are by mass. So we can infer what's the contribution to the cosmic star formation history of galaxies that today are blue, red, Green Valley, and of different masses. It's very difficult to see this plot, but all the information is there.
Question from online from Gaspar Galatz.
Yes, thank you. Congratulations, Vladimir. This is an awesome work. Huh? It's very interesting. There are many things to see here. I have a question regarding the S0 galaxies. You are very successful to separate, of course, ellipticals and spirals, and to see many properties among them. But I missed a little bit about a word about the S0s that could be very important, specifically for the Green Valley you observed there. Do you have something to discriminate the S0 population? And do you observe different things or any signature that is different from the S0s to the ellipticals, for example?
Yeah, we didn't specifically study as a subsample of S0 galaxies, but in general, I can say that the S0 galaxies typically are in the Green Valley. I I think I have this plot. No, I don't have this plot here. But very, very generally, there is more or less most of the S0s are in the green valley. There are S0s quenched or star forming, but most of them are in the green valley. But we didn't, especially as, for example, with the ellipticals, analyze all the evolution, all the things that I presented for ellipticals, for example. But I agree that it's very interesting to study in more detail this kind of lenticular galaxies. There is other group, I think, there are other groups in the MaNGA collaboration which are working specifically with lenticulars. There are others that are specifically working with barred galaxies, for example, or even with the ring galaxies. Yeah, so there are a lot of work to do, in fact. But with the lenticulars, I think that is all that I can say right now. Yeah.
Okay, thank you very much.
So, Gaspar? Any more question? Okay, so let's thank the speaker again.